You. Yeah, there's no off days until Thanksgiving.
I would check
So today we're going to take a look at blood gases and acid-base balance, which is more of a follow-on to last week's talk on pulmonary function, since pulmonary function is so important in terms of blood gases. And then we'll circle back to, there were still a few slides on the hematology before going on to blood coagulation next week, okay? So blood gases, and what better than a big bag of hot air up there to kind of introduce the topic or whatever. Maurice Prendergast was a native of Newfoundland, St. John's, Newfoundland, and had extensive training by the Impressionists in Paris before moving to Boston, and basically spent the rest of his life in Boston painting in this post-impressionist type style. So you can again see bright colors, maybe not the most appropriate in terms of reality, but makes a statement. And that's what we see in post-impressionism, with heavier strokes and palettes than in the Impressionists, which were much more lighter for the most part. And so again, blood gases, respiration, pulmonary function. We're going to just kind of touch acid-base balance. It's a little bit more involved, but we'll just kind of introduce some of the concepts, and then later on in a number, you'll probably see in about 3 or 4 different classes, because it's a big deal therapeutically. And so we're just going to kind of introduce some of the concepts or whatever today. So if we're going to look at blood gases, we're primarily interested in carbon dioxide and oxygen in terms of the actual gases themselves, but we'll also look at pH and bicarbonate, because it's really the combination of all of those parameters which will determine the availability of oxygen to the tissues, as well as the appropriate pH environment of the blood. And so, as you recall from biochemistry, the Henderson-Hasselbalch equation deals with essentially bicarbonate, carbon dioxide, carbonic acid, and pH buffering capacity. And so that's essentially what we're looking at here, is just some of these parameters that go into this major buffering system for the blood. So we are going to look at arterial blood in this case. Unlike most of the blood values, clinical chemistry values that we use, which come from venous blood. So for sampling, you need to sample from an artery, and generally the radial artery is the most easily accessible, and so that's what we're going to be looking at. So some of the values are primarily the bicarbonate, as you'll see, is not going to be exactly the same as the venous side, but that's fine. I mean, that's just reflective of the difference in terms of blood that's perfusing tissues versus blood that is essentially draining from those tissues. So arterial pH should, in the normal range, is 7.35 to 7.45, and it is kept within that range for the vast majority of time because of the impact of pH changes, not only in terms of what's given here, which are primarily physiologic changes with regard to tissues. So there's changes in arterial dilation, venous dilation or constriction. The myocardium is particularly sensitive to pH changes, things of that sort, but also a variety of different chemical reactions and equilibria that are based on having a pH of 7.35 to 7.45. So if you start to deviate significantly from that, you can start having metabolic problems in addition to physiologic problems. And one of the major considerations with regard to physiologic effects of this change in pH is on the oxyhemoglobin dissociation curve and the availability of oxygen, therefore, to the tissues. So this diagram here is showing on the x-axis, so that's our arterial blood gas determination of oxygen, and on the y-axis, the oxyhemoglobin, or the percent saturation. And so the normal curve is the blue one in the middle. And if the pH drops, or DPG, which is a red blood cell, basically energy dependent substrate, 2,3-diphosphoglycerate. If that increases or the temperature increases, then we'll see what's called the Bohr effect, which is a shift in the dissociation curve to the right, meaning that for a given saturation of the hemoglobin, you need a higher partial pressure of oxygen. Conversely, an increase in pH, blood pH, reduction in DPG or temperature will shift that curve to the left, and so saturation is achieved with a lower oxygen tension. So with regard to the the ability of the tissues to extract oxygen, it's going to be pH dependent, and we'll see situations where one needs to supplement oxygen because of the metabolic condition, the shift in pH. So, so pH clearly is a significant factor. And another one in terms of blood pH and oxygen and the overall ability of the system to deliver and extract oxygen and CO2 would be the partial pressure of CO2. Normal range down around 35 to 45 millimeters of mercury. And we think of partial pressure or PaCO2 essentially as an acid, because there's that equilibrium between CO2 and carbonic acid, which naturally there's a equilibrium between those two. as well as we can force the reaction one way or the other with carbonic anhydrase. But so whenever we're going to see increases in PaCO2, we're going to think increases in carbonic acid, and with that, a reduction in pH, all things being equal. And of course, there's a lot of compensation that can go on. But so anything that's going to increase, the amount of carbon dioxide in the blood. So if a person is hypoventilating, for example, then you're not blowing off CO2, and so blood levels will increase. So that's one mechanism for that. And we'll see others which are connected. And one of the things about this whole acid-base system is the connectedness between respiratory and metabolic regulatory systems. The metabolic regulatory systems primarily being handled by the kidney, obviously ventilation by the lungs. Partial pressure of oxygen runs about 80 to 100 millimeters of mercury. And in terms of when an individual would be considered hypoxemic, which would be impaired oxygen levels, it is, somewhat contextual because of the different factors that really go into determining what arterial partial pressure of oxygen is. So one clearly is ventilation. So how rapidly is the person inhaling and exhaling? Another factor would be the fraction of inspired oxygen, the FiO2. And so under normal conditions, the percent of oxygen in the air is about what? 21% is what's generally used for FiO2 as a, so the fraction, and again, that's going to be somewhat dependent on elevation, but 21%. So a person who might be hypoxemic, you can provide them with higher percentages of oxygen rather than room air, and that'll enhance PaO2 at the same level of ventilation. The functional capacity of the lungs, how well that they can expand. So various pulmonary diseases like COPD, interstitial fibrosis, all those things can change the capacity of the lungs to expand and take in the normal volume of air. And then the oxyhemoglobin dissociation curve. Again, how much of that oxygen is going to be carried by the red blood cells, because very little dissolved oxygen is present, just in terms of oxygen within the aqueous compartment. It's being carried by hemoglobin, and with hemoglobin and oxygen saturation, right, we're looking at 4 heme molecules per hemoglobin molecule, so that's 4 oxygen molecules that can be carried. And so oxygen saturation is related to PaO2, but it's not the same as PaO2, because the saturation is dependent on hemoglobin as well as the amount of oxygen that it is being exposed to in terms of the ventilation aspect. So for this oxygen saturation, we're looking at the percent of hemoglobin binding sites that are occupied with oxygen. And again, 4 heme molecules, so 4 oxygen molecules per hemoglobin molecule. And already talked about that the dissociation of that oxygen is pH dependent. And in general, for most people sitting here today, their oxygen saturation runs someplace around probably 97 to 100%, something like that. 95 to 100% is considered kind of, normal. Actually, all the way down to low 90s. Still, you're not going to do anything about it. It's just a little bit on the low side. When you get below 90%, then considered low and might need to start considering something there. But we monitor oxygen saturation not by really taking a blood sample or something like that. But we use a pulse oximeter. If you've seen anybody that has been in say a hospital or something of that sort, and they clip a little device onto their fingertips, that's a pulse oximeter, just basically laser that it looks for the relative absorption in the red versus the infrared region, which is basically the shift that occurs in hemoglobin absorption in these ranges as a function of oxygenation. And so it's a very simple kind of optical measurement that can be done. Give it a number. Yeah. It's going to come up. There it comes up. Yeah, see? Question about that oxyhemoglobin dissociation curve and pH. And so for arterial blood for pH less than 7.35, we'll see a shift which way? Or no shift. Shift to the right and down a little bit. The Bohr effect, not the Haldane effect. Okay, so arterial bicarbonate. So this is really a calculated value and is reflective, certainly, or the venous bicarbonate is going to be reflective of the arterial, but they're generally a little bit different. And we'll just use the arterial pH and PaCO2 and the Henderson-Hasselbalch equation to calculate a bicarbonate, and it should be within about 1 to 3 milliequivalents per liter of the serum bicarbonate. So,
I just have a question. Are you going to expect us to calculate that?
I hadn't thought about that. You shouldn't have brought it up.
Thanks. I'm just curious.
I wasn't planning on it, no.
Yeah,
But that was from biochemistry, right? You've calculated with the Henderson-Hasselbalch in biochemistry, haven't you? Yeah.
8 years
No?
ago, maybe.
Never heard of it.
Okay. Well, so, I mean, I wasn't planning to going through it, and but it's basically just the, the equilibria equation for bicarbonate and carbonic acid, and from that you can you can plug in the value for pH, you can plug in the value for bicarbonate, carbonic acid based off of what the PaCO2 is and come up with a bicarbonate. But no, I'm not going to do a calculation on that. Although for future classes, that's not going to do. Anion gap.
That's fine.
Another calculated value to try and get an idea about how the body is responding to a change in pH. And it's really using some measurements that we do routinely, like what's the sodium level, what's the chloride level, what's the bicarbonate level, as a way to look for other ions that we don't calculate or analyze for directly, but which could be impacting the pH, okay? So the anion gap is in general between 3 and 16 milliequivalents per liter, and it's essentially this little equation down here. So it's the cations, sodium, minus the two predominant anions, chloride and bicarbonate. And that difference is what should be 3 to about 16 milliequivalents per liter. And if it exceeds that, then that suggests that there are other ions in there and very likely are impacting pH. And so things like lactate, ketones, certainly if there was some kind of toxin that was a strong acid or base that was ingested, would be reflective in an anion gap exceeding normal because it's contributing to the ions, but we're not directly measuring it. But these sodium chloride, particularly the chloride, will respond to the presence of these other ions. So we'll see these, for example, when we have a metabolic condition like diabetes that's not being adequately controlled, and or a situation where the body goes into anaerobic metabolism. That's basically what happens with a diabetic situation. Then all of a sudden you start to produce lactic acid, and that gets into the blood, and it's going to impact the pH because it's an acid. Yeah.
Is there a reason why the range is so huge compared to other previously given values of the things? The background doesn't really and low in the high.
I guess I'm not going to follow. Oh, you mean why there's such a big gap in here?
Like 10%, you know.
Oh, I see what you're saying. Yeah, well, here, because it's a lot of different things that ions and metabolic conditions, which can impact us, and so, but under normal conditions. So things that people eat, the degree of hydration, a variety of things can impact that. So it's pretty broad because of that situation. It's not under as tight regulatory control as many of the other parameters. Yeah. So under a specific condition, we do have to correct the anion gap because serum albumin does have an impact. So a situation where, for example, a person is hypoalbuminemic, a situation where there is, for example, liver injury, and so the production of albumin has decreased, is enough to skew these values And so you'd have to put a correction factor. So basically, if you see a situation where a person is hypoalbuminemic, you first calculate an anion gap and then correct for the drop in albumin. And it's essentially for every gram per deciliter of albumin, there's a change in the anion gap of about 2.5, okay?
White.
So albumin is obviously a very, it's present in a high concentration in the blood. And in terms of its charge density, it has an impact on the overall ionic strength of the plasma of the serum. So it's the one protein that really can have an impact. So, you know, this can be significant enough to suggest that there's, you know, an anion gap that may just be, say, borderline, but if you adjust for albumin, it'll become a significant excursion outside of the reference range. The anion gap, in addition, can be impacted by phosphate, some of the other ions, but you really need to get some significant changes in those. So it wouldn't happen under, you know, most circumstances that there's not enough of a change in magnesium and calcium and phosphate really to impact it. But for some clinical conditions, again, that might have to be taken into consideration. And so there's additional corrections and alternate formulations of this anion gap if you have some of these other conditions. So regulating the acid-base balance. In terms of production of acids, metabolically, we produce a lot of acid. And we also produce a lot of CO2, which again is going to, in equilibrium with carbonic acid, be acidic as well. So 15,000 millimoles or 15 moles of CO2 per day. And that doesn't, again, include any of the metabolic byproducts that are acidic that are produced. And the pH of the blood varies by less than 10 nanoequivalents per liter, okay? So very tightly regulated. And we do it primarily through the lungs, through the kidneys, and the presence of buffers, primarily the bicarbonate buffering system. Although some of the amino acids, for example, are you know, moderately good buffers themselves, but the vast majority of it is the bicarbonate buffering system. So the normal equilibrium for these different reactions or equilibria can be adjusted based on the presence of carbonic anhydrase. And where do we find carbonic anhydrase? We find it in the liver. In the liver. No, we don't. We find it in the kidney. So particularly the proximal tubule of the kidney is very enriched in carbonic anhydrase. So a lot is going on in terms of CO2, bicarbonate, recovery, things of that sort in the proximal tubule. It turns out actually that there's another site for carbonic anhydrase, and this is totally a digression, and that's in the eye. There's certain, and it's involved in the production of the aqueous humor, and with it, for people that, for example, develop glaucoma, which is an increase in the eye pressure because of the, well, there's different types, but anyway, production of this fluid, which is driven by carbonic anhydrase. You can use inhibitors to treat glaucoma using these carbonic anhydrase inhibitors in the eye. But the primary, the big source is the kidney, K-I-D-N-E, not liver. Okay. So, kidney for bicarbonate, CO2 in terms of the lungs. So, and we're going to regulate those. Ventilation certainly is regulated by the central nervous system, by certain sensory receptors that we have, chemoreceptors, that depending on the amount of carbon dioxide that is present in the blood, that will get varying levels of outputs to enhance or inhibit respiration. So clearly, increases in CO2, PaCO2, you're going to start to increase the respiratory rate and try and blow that CO2 off, okay? So that can happen within minutes. For adjusting bicarbonate, it's going to take a lot longer because that's going to depend on that those cells in the kidneys for changing the amount of CO2 that is taken up by conversion of bicarbonate and re-equilibration of a variety of different equilibria. So respiratory regulation, that's our fast regulation, and it's adjusting the ventilation and the clearance of CO2. Renal regulation. So lots of milliequivalents of bicarbonate is being filtered. It's a small molecule, so it gets into the glomerular filtrate very readily. And we don't want to lose it all. So in that proximal tubule, we're going to reabsorb it by carbonic anhydrase on the luminal surface of the proximal tubule epithelial cells. Will essentially take bicarbonate that has been filtered, add a proton. We generate carbonic acid, which is then going to be dissociated into CO2, and that will diffuse across the cell membrane. And then on the, basically within the cell, we'll go through the reverse process. And so you take up your bicarbonate as CO2 because of this carbonic anhydrase mediated process. And then it'll be returned, it'll be pumped out of the these epithelial cells back into the blood, and so we capture 90% of what gets filtered. Yeah.
So basically, the red blood cells are like more important than like the kidney terms, because everything's going to be coming out of CO2, correct? Like 90% of the reabsorbed in the kidney is still going to come back through the lungs and like the exhale the CO2.
So we'll be correct. but in terms of being more important than the red blood cell, I was just trying to, why do you say that? I mean, what you said is true in terms of, well,
So the red blood cells carry back the CO2 to the lungs. That includes the bicarbonate that's been broken down to CO2 that the kidney has already worked on to absorb.
so,
Like my original question was really like in terms of like an anemic patient, like if you have a low red blood cell count, how does that affect your acid base balance?
so does, it would have to be, theoretically, yeah, you're going to start to have an impact. But you'd have to be severely anemic for it to have a major impact on acid-base balance. So much of it is regulated through these buffers that are stuff. But I can see, yeah, and eventually you can get to a state in which you're going to have some disruption in terms of gas exchanges that would have an impact, but it's going to have to be a very severe anemia. So, just, I guess, keeping in mind that we are making these other metabolic products that in general are acids, releasing those into the circulation, and they can have an impact on overall acid-base balance. A lot of the non-volatile acids are neutralized by the bicarbonate. And so we can handle the general production. It's only when there's a metabolic condition that leads to a disruption in the, either the bicarbonate or some of the counter ions that you have, the potential for a change in blood pH. And again, coming back to anaerobic metabolism is probably one of the most common causes for this. And because of the production of lactic acid in particular. But you can see here that if there is an adjustment in terms of the production of organic acids and a build in an anion gap, that it can take days for for the full compensation by the kidney to occur. It's not going to happen in the minutes to maybe an hour or so. That can occur through ventilation. So when we're going to look at acid-base disorders and try and understand arterial blood gas values, we're essentially dividing things up into 4 different compartments. You have acidosis, you have alkalosis, and then you have the cause for the acidosis or alkalosis as being either respiratory or metabolic. So you end up with either, respiratory acidosis, respiratory alkalosis, metabolic acidosis, or metabolic alkalosis as primary causes for acid-based alterations. And in terms of, kind of making sure that you have the right primary mechanism, it's kind of a step process to look at. So clearly the first step is the blood pH greater or less than 7.35 to 7.45? Less than 7.35 is acidosis, more than 7.45 it's alkalosis. So that's pretty straightforward. Then is it respiratory or is it metabolic? And if it's respiratory, then for a primary respiratory acidosis, we're going to expect the PaCO2 to be greater than the norm, because that is yeah, okay. High PaCO2 is going to be high carbonic acid, which is going to be a lowering in the pH. And conversely, you're going to have the low PaCO2 for respiratory alkalosis. So what is the PaCO2 in this individual that has, this change, the pH either high or low? Metabolically, focus on bicarbonate, so in the sense that a primary metabolic acidosis is going to have low bicarb, because that's normally there to neutralize acids, and so low levels of the bicarbonate would be and a low pH would be consistent with the primary metabolic acidosis, and conversely for the metabolic alkalosis. So it's a contextual thing, and as we'll see, for the next step is to try and confirm this based on anion gap, or how the body is compensating. Yeah.
I just want to verify. So the values you present up here with the 40 milligrams of 20 milligrams of mercury PaCO2 is different from the normal values presented on the earlier slides. It was at 45, 45. Are we using the 40 or the 45?
So use the 40, because again, this is in the context of a low or high. So these values are for higher or low pH, not within the norm. Okay, so even though it may not exactly line up with what those other ones are, which are in the normal reference range, it's because contextually it's now a different. You're at a different state or a different level, and so and at the same time, what's happening is that you get both adjustments in terms of the system trying to compensate, and that will bring some of these values back almost into normal range potentially, even though other ones are out of range. So use these values.
And do we have any values for we have values for high PaCO2 but not low? Or do we have values for those?
So that would be, so use the low end of the normal range for those. Yeah. So compensation is a big part of this, because as the system starts to go out of where it wants to be in terms of pH, it will start to compensate. And it can do it by respiratory mechanisms. It can do it by renal mechanisms. And in general, both are probably going to play some role in the compensation. And so that's where we'll start to look at anion gap and what that is doing in the context of these other values, okay? So if you see a metabolic acidosis based on what the pH is, what the bicarbonate levels are, then if we do an anion gap calculation, then there'll be values that will probably exceed 16, okay, if in fact there's a true metabolic acidosis. And in terms of these mnemonics and things like that, don't worry about what they stand for or anything, because all I'm going to say is we'll just focus on basically, diabetic ketoacidosis or salicylates as two examples of condition, one being a metabolic condition that clearly produces significant changes in blood pH. And the other one is a therapeutic agent, basically aspirin, which will do the same thing, okay? And a person who takes a significant amount of aspirin can drop their blood pH enough to start causing neurologic problems, and that's basically the major and potentially life-threatening, although you really got to take a boatload of it, to get to the point that you're going to have, go into a coma or something of that sort. But those two are kind of classic mechanisms for producing metabolic acidosis, okay? If there's a metabolic alkalosis, so the blood pH is on the high side. One of the common causes of that is the loss of chloride, but actually the proton associated with it, so hydrochloric acid, through vomiting or severe diarrhea, something of that sort. So essentially what happens is that because there's so much acid that's being lost, protons being lost, and many times with the chloride as a counter ion through the GI tract, that metabolically or within the person, they shift the whole pH. There's not enough acid to compensate for the production of alkali material. So if the urinary chloride falls to less than 25 milliliters, then it's considered a chloride-sensitive metabolic alkalosis, because you could treat that person with saline and essentially replenish chloride, and with it start to reestablish the ionic relationships that have been distorted because of the loss of chloride through the GI effects. In contrast, at high levels of chloride, that says, okay, that's not the way it's working. We're not going alkali because we're losing all of this acid through the GI tract. It's because we're presumably being exposed to, for example, hypercalcemia, so high levels of calcium, and with it, the shifting of the amount of hydroxide ions and things of that sort. So it's a different type of mechanism, and it's not because that we've lost chloride. So you don't treat that type of alkalosis the same way, because there's no problem in terms of chloride, okay? So those will be, I mean, in terms of the different types of metabolic disorders and the different causes. I mean, we're not going to go, that's about as far as we're going to go down those rabbit holes. Metabolic acidosis, we're going to see low bicarbonate, and we're going to see obviously low pH. And this is, again, things like production of keto acids because of anaerobic metabolism, the ingestion of some kind of acidic compound, things of that sort. Respiratory acidosis, hypoventilation is primarily what's going to cause it. And so a person who might have some kind of obstruction or low capacity of the lungs, something of that sort, so that they can't exhale sufficiently, move the air so that you get rid of the CO2. Obviously, in that situation, you have to compensate metabolically for that. So bicarbonate will compensate, but it's going to be a slow process. Generally, we'll see this, potentially the people are also hypoxemic because they're not ventilating well. And that is a comorbidity at the same time. Respiratory alkalosis, a person who hyperventilates. So people that are extremely anxious, people that have a fairly high fever, they'll start to hyperventilate, and with it blow off a lot of CO2. That's going to be obviously producing this alkalosis, and with it renal compensation. That's going to take a while. So this is where, depending on the exact mechanism, you might be able to compensate on the respiratory side of things. That's where you have the person, for example, inhale higher concentrations of CO2. We really don't have time to do this. Take a look at this, and there'll be a homework next week that'll be basically a case like this, similar to what you just did for the hematology one, okay? But here again, the steps, you're gonna look at the pH just quickly. So the pH is low, so it's an acidosis. We're gonna look at the gases and the bicarbonate to see what's causing that. We do know that she had severe diarrhea, so chances are we have a problem in terms of a metabolic rather than a respiratory cause for this. And you can go through the rest of it, and I'll maybe next time go through the actual numbers and things like that for you. Okay? So, any other questions? Seeing